Greetings everybody. This video will hopefully explain how to do, there's three examples I posted um, where you have to solve them using Newton's second law. And if you go to the Georgia View page here in the chapter 4 module, you'll see I have here, and again I post everything in Word and PDF format, just for convenience. So here you'll see I have homework problems, Newton's second law. And there's three problems. There's the hanging traffic light problem, then the hanging cement bag problem, which is really exactly the same. Problem 3 deals with two connected masses, connected via a frictionless pulley. And then problem 4 is the sliding hockey puck. So there's four problems where you have to solve them applying Newton's second law. And then notice I've also posted my worked out solutions, but what I'll do is I'll go over the solutions. I'll probably break this video up into 2 or 3 parts, again, to keep the size manageable. Alright, but again, if you go to the Georgia View page, go to content, then you go to chapter 4 module, and there are the notes, videos, and now there are homework problems, Newton's second law, and then homework problems, Newton's second law key. Alright, so we got that. So let's look at the first problem. So you have a traffic light and it's hanging in equilibrium, which means, of course, that it's the acceleration is 0. The traffic light is not moving, and it's hanging from a cable, and the tension in that cable supporting the traffic light, we'll call that T3. And then 2 other cables. Then the third cable, whose tension is T3, is attached to 2 other cables whose tensions are T1 and T2 respectively. And notice from the support, T1 and T2, T1 makes an angle of theta 1 with the support, T2 makes an angle of theta 2 with the support. And notice those angles are not equal, which is fine. But so theta 1 is 37 degrees, theta 2 is 53, and we know that the traffic light, it weighs 122 newtons. That's what mg, when we say an object weighs a certain number of newtons, what we're saying is mg equals 122 newtons for the traffic light. And then the upper cables will break if the tension in either one of them exceeds 100 newtons. And so we want to know, does the traffic light remain hanging, or will T1 or T2 break? Well, cable 1 and cable 2, I should say. T1 is the tension in cable 1, T2 is the tension in cable 2, and T3 is the tension in cable 3. And again, the cables 1 or 2 will break if T1 or T2 exceeds 100 newtons. So obviously we need to calculate T1 and T2. Now in this case there are 2 objects involved in this problem. One object is the traffic light. The other object is see this black dot? That's the knot where the 3 cables are connected. So we have to apply Newton's second law to those 2 objects. The first object being the traffic light, the second object being the knot where the 3 cables are connected. And that's very standard. Again, when you do the cement bag problem, what are the 2 objects in equilibrium? Well, one object is the cement bag itself, and the other object is a knot where the 3 ropes are connected, right there. So, and here FG, the book that I got this figure out of, FG is the same as MG. So there's some books, they're saying that's the force. The subscript G means that's the force due to gravity, i.e. that's the weight. So Fg is simply mg when we get to that problem. All right, oops. All right, so let's go back to problem 1. So the 2 objects again are the knot that connects the 3 cables, that's one object, and the traffic light. Let's go ahead and apply Newton's second law to each of those objects. Okay, and again, our goal is we need T1 and T2. We need to find out if they exceed 100 newtons. Well, first, let me apply Newton's second law So again, I need to apply Newton's second law to the traffic light and to the knot. Let me do the traffic light first. And you can see right here, here's the traffic light. And again, we have to draw all, no matter what the object is, you have to draw all the forces acting on the object. Well, what two forces are acting on the traffic light? Well, there's the weight of the traffic light, mg, pointing in the negative y direction. We know that mg is 122 newtons. Okay. Now remember, the traffic light is attached to cable 3. So there's going to be, we'll call the tension force in cable 3, very logical. We're calling that T3. Well, remember, the tension force points along the cable but away from the object. So notice T3 is in the positive y direction. Now remember, both the knot and the traffic light are in static equilibrium. They're not moving, and obviously they are not accelerating. Okay, so we know that. Okay, so now these are the two forces acting on the traffic light. T3 is in the positive y direction, mg is in the negative. Now remember, traffic light is in equilibrium, meaning that these two forces have to be equal. And the long way to write it is, again, we're just dealing with the traffic light. Because it's in equilibrium, we have the sum of the forces in the y direction. There's only two. That sum must be equal. It must equal 0. Well, T3 is positive, mg is negative. Obviously, just look at the figure. So T3 minus mg equals 0, i.e. T3 equals mg. And we know that mg is 122 newtons, so we know that T3 is 122 newtons. Okay, so now we're done with the traffic light. Let's go ahead and let's draw all the forces acting on the knot. And then let's break them up when necessary, break them up into their components. Well, the three forces acting on the knot are the tension force T1 in cable 1, the tension force T2 in cable 2, and the tension force T3 in cable 3. Well, we know T3. Now notice T1 and T2, clearly, each of them, both T1 and T2, they each have x and y components. Well, the trigonometry is fairly straightforward. Notice if this angle here is theta 1, the angle here, the angle that T1 makes with respect to the x-axis, that angle is also theta 1. Likewise, for theta 2, if this angle here is theta 2, then the angle that the vector T2 makes with the x-axis, that angle in here, that is also theta 2. And so so let's look at T1 first. The x component of T1 is T1 cosine theta 1. The y component of T1 is T1 sine theta 1. Likewise for T2, x component T2 cosine theta 2, y component T2 sine theta 2, as indicated by the figure. Well, now remember, the knot is also in equilibrium. So to make a long story short, because it's in equilibrium, obviously the two forces in the x direction, one's negative, one's positive, they have to equal each other. So we know right away that T1 cosine theta 1 equals T2 cosine theta 2. Oh, and let me just go back. Right here, when I have T3 equals mg, that's equation 1. See that I'm numbering, that's equation 1. Now here, when I get T1 cosine theta 1 equals T2 cosine theta 2, that's equation 2. Now let's apply, again, now the knot is in equilibrium. Let's look at the y direction. Well, T1 sine theta 1 and T2 sine theta 2, they're in the positive y direction. T3 is in the negative y direction, and we know T3 is mg. Well, remember again, the knot is in equilibrium. So again, we're now looking at the y direction. The two positive y forces must equal the negative y force. So T1 sine theta 1 plus T2 sine theta 2 has to equal T3, which is mg. That's equation 3. Okay, so now we have three equations. Well, we have two equations and two unknowns. We have equation 2, T1 cosine theta 1 equals T2 cosine theta 2, and we have equation 3. T1 sine theta 1 plus T2 sine theta 2 equals mg. So that's our two unknowns are T1 and T2. Well, we're happy. Mathematically, we're happy. Two equations, two unknowns. Now, again, the easiest way to solve this is let's solve equation 2 for T2. Then the expression that you get, you take that expression for T2 and put it into equation 3. So again, so when I solve equation 2 for T2, it's very simple. Just divide both sides by cosine theta 2. So T2 is T1 cosine theta 1 divided by cosine theta 2. Where does this expression go? This expression goes into equation 3. I'm going to put it in right there for T2. That's what I'm doing right here. Right here in equation 5. This term in parentheses, that's the expression for T2. Okay? Well, notice, so I have T1 sine theta 1 plus parentheses T1 cosine theta 1 over cosine theta 2, close parentheses, times sine theta 2 equals mg on the right. Well, notice, sine theta 2 over cosine theta 2, that term right there, sine over cosine, sine theta 2 over cosine theta 2, well, that's tan theta 2. So I can replace the sine theta 2 divided by cosine theta 2 with tan theta 2. See, in the purple. Okay, so now I have an equation where the only unknown, this equation here, the only unknown is T1. Algebraically, if you solve that equation for T1, you get this expression. You get T1 equals mg divided by sine theta 1 plus cosine theta 1 tan theta 2. You know mg, you know both the angles, so you plug in the values and you get T1 is 73.4 newtons. Underneath the threshold, it's less than 100. Now T2, remember, equation 4 gives us T2. Once we get T1, we use equation 4 to get T2. T2 is just T1 cosine theta 1 divided by cosine theta 2. You know T1 from the previous part. You know the angles. Plug in the values, you get 97.4, less than 100, so the cables won't break. And this is a very common technique where we have equations 2 and equation 3. So we have two equations and two unknowns. And so solve equation 2 for T2, getting out that algebraic expression you get for T2, you plug that into equation 3. And then very straightforward from there. In the second term on the left right here, you have sine theta 2 divided by cosine theta 2. Well, that's tan theta 2. So that sine over cosine is now the tan in the purple. And then just, then from there, solve for T1. All right. So this video's a little over 13 minutes long. Let me go ahead and save this video and get it posted.